associate and then as a senior research associate in the Max Planck Institute for Biophysical Chemistry in Germany. And in 1998, he came to University of Illinois here in Urbana-Champaign, where he is a professor in the Department of Physics and the Center for Biophysics and Computational Biology. And he's using fluorescence, dynamics, and laser imaging to study physical basis of molecular interactions in biological systems.
Okay.
Mr. Clegg?
Yeah, thank you, Marina. And so you've had a really nice introduction from Ben on the modern way in which we look at fluorescence. So what I'm going to do is take you back, okay, to how people got these ideas in the first place. And as a matter of fact, what we're going to see is that people got the wrong ideas, and very famous people got the wrong ideas, which you have to remember in your future when you get into things. You can feel if you make mistakes in your research and you publish something that's wrong, there's some very famous people that have done that before. Okay, and we'll see that as we go through just a little bit. So first of all, I'm going to talk about the history, and I say here trials, blunders, tribulations, because it wasn't easy for people to get the idea of what a fluorescence lifetime is. Then I'm going to talk about what is a lifetime anyway. Ben told you more or less how you measure the lifetime and how it's used, but what really is it? And we'll find out that that was never solved for a long time. Now, for a long time, ancient times, things like that, obviously light has been around for a long time. This is a very old account from 1887, where we've had bioluminescence, some chemiluminescence, but essentially bioluminescence. That's what Ben actually referred to with the wood. And it's been around for thousands of years. And actually, I'm sure people noticed it even tens of thousands of years ago, because you can be on an island. Those of you who may, I don't know how many of you have been there, you can be on an island and you can see it in the ocean, and you can see the luminescence come in the ocean at night, right? You can also walk on a beach, and when you walk on a beach, you see those little animals emit radiation. So it's been around for a long time. Chemiluminescence has also been around for a long time. It's sort of interesting just to say the idea of phosphorescence, which he was talking about, comes from phosphorus. Phosphorus was the ancient name in Greece for Venus, the planet. And interestingly enough, phosphorus was first of all distilled from urine. The reason in urine was people noticed that urine had sort of a gold color. People were very interested in getting gold, so they distilled urine. And they didn't get gold, but they got phosphorus. And it's not a real, it's a chemiluminescence, because what happens is that when you actually distill and then separate the phosphorus and then let it come into contact with air, it luminesces like this, and you get a very bright light. Okay, you can do that. Now, the first example, I think, of luminescence that was excited by light was actually quite famous. And this was a long time ago, in 1603. And I like the way this is actually written in this paper. You used to be able to write papers like this when you read about, a certain cobbler walking down a narrow winding street of an old town of Bologna, which unfortunately is the town that they just had this big earthquake with. He discovered in 1603 that if he went to a certain hill outside of Bologna and he picked up a stone, and the stone was a little bit heavier than normal stones. Aha, so gold's heavy, right? So he brought it back to his laboratory. He was a cobbler, but he was an alchemist also, as a lot of people were at that time. And he mixed this with certain things, put it into an oven, and when he extracted it, he actually got a material which is now, which it says here, absorbs the rays of the sun by day to emit them by light. And this is the first indication I know of a lifetime. Okay, the fact that if you excite something with light, in this case the sun, he could actually bring this material into a dark room and read for a few hours, because it was luminescing over a long time. And as a matter of fact, it was actually shown to be a curiosity. It is known as solar phosphorus in the Bologna stone, but was also then known as the philosopher's stone. And a lot of people went down into Bologna to look at this stone because it had some sort of magical properties. This is a picture of what it looks like in one of the museums in Bologna. And I have to remind Ben, but I've always told people when they, especially if they're Italian, which Ben is, you go back to Italy, please go up to Bologna, go on that hill, take a piece of stone and bring it back, because I teach a class in fluorescence and I would really like to stick it in an oven with the right stuff and, and make it here, but I haven't been able to get it yet. I guess I'll have to go myself, right? And pick it up. That'll make a nice NSF grant. They're going over. Okay, now, this is interesting that one of the people who went down to Bologna was Goethe. Goethe was sort of the Shakespeare of German literature. And it is interesting that he says in one of his first books when he was a young man, The Sorrows of Werther, that the Bologna stone, when placed in the sun, attracts the rays, retains them so long to give light a considerable time after it is removed from the dark. There you go. It's a lifetime, right? And he could measure that, and he noticed that and wrote it. Interestingly enough, when he wrote it in this story, it had to do, he had a mistress, and his mistress had left and gone somewhere else, and I mean in the story, and so he sent a boy with a message to his mistress because he couldn't wait a few days, and then the boy came back with another note, and he's supposedly looking at the buttons on the coat of the little boy who came back from giving the message to his mistress, and he imagines that it is radiating with her love for him as the Bologna stone radiates over a long time. So there you go. Okay, that's the lifetime of something else. Okay, so now we have the first quantitative measurements of luminescence was actually done a long time ago by Becquerel, the person that we know mainly for radioactivity. Now, he did this quite a long time ago, and it's pretty clear what it is. He's got a wheel that's rotating really fast. He has a light, so he can excite things, and then he can look at something in the dark after he's excited it with light. You can see it on the next slide here. That's what he's doing. He's rotating this thing really fast, and then he's looking at it after it has been excited, but when it's not actually being excited anymore. And it was known as a rotating mechanical chopper, so he has the light on for a while, and then he has a certain time when it's dark, when there's no light on, and he can look during this time. And actually, he could also see an image, so he was seeing those. Now, he can only do that so fast. It wasn't nanoseconds like we're talking about now, but it was a long time. But there's a couple of interesting things in his early papers that you read. And one of them is that, first of all, he was interested in two exponentials. Well, let's say, first of all, the most important thing is he realized that it was an exponential decay. At least that's what he wrote down. It made sense to him. Remember that, because that idea is going to get lost, okay? And people are going to get mixed up. For a particular reason. But he also, even at that time, was worried about double exponentials, and he realized that if he integrated that over the long time, he would get something this is the rate of 1 over the lifetime that Ben was talking about. And so this is actually the total amount of intensity that you get in a steady state fluorescence when you excite something. So he had a lot of information from there. He was looking at minerals, not at fluorophores. And by the way, I was going to say in the beginning, if any of you, as I go through, we're going to go through a lot of concepts and everything else, and if you have any questions or if I went over something too fast, because I realize when I get going I talk rather fast, so please go ahead and ask questions, okay? Okay, now let's see what we see when we see nanoseconds. How do you do that? That was a very, very difficult thing to do at that time. And it took a really good experimentalist. So we look at one of the best experimentalists in the world around at that time. His name was Wien. He was very famous for the black body radiation. It was called, he had a theory for the radiation. He did a lot of other things. He was one of the, not discoverers, but the inventors of mass spectrometry, things like this. He was known for the Wien displacement law, which some of you probably remember in some of your courses. Very famous guy. Actually, it's interesting that we all know Heisenberg, right? Heisenberg and Schrodinger from quantum mechanics. Actually, Wien flunked Heisenberg on his final thesis exam because Heisenberg couldn't explain anything about experiments because he didn't care about experiments. And so he gave him an F because he couldn't explain how a battery worked. And the other one, Sommerfeld, who was his actual PI, gave him an A, or 1, and then sent him off to Max Born. And Max Born in Göttingen, when Heisenberg came to work with him, took a look and he says, "This guy's got an average of a C. What are you sending me?" You know? And Sommerfeld said, "You know, take it easy, go ahead. He's really good." And but he was pretty stubborn about that. If you didn't know experiments, you were out. Anyway, so he was an extremely good experimentalist, and what he did was he wanted to look at, you notice that this was done in 1919. Well, in 1917, and I don't have a slide for that right here, Einstein had told us what the lifetime would be. He did this by what's called his A and B coefficients, which were completely calculated theoretically without quantum mechanics, no model, but thermodynamics, okay? He had a particular type of a model that he used about thermodynamics, and he told people what the lifetime should be. So it was interesting for people to try to see that, and what he had was here, he had a heater, and he had different types of material. In this case, we'll see it's mostly hydrogen atoms, and that would heat, and he had a manometer went to a diffusion pump, so this was a vacuum up here, and the atoms would come out going very, very fast. And he knew how fast they were going because he knew what the pressure drop was across here. So then he would excite them up here and then look in this area up here at how the luminescence disappeared. Okay, so he would have a light that would shine when it was going here. So rather than making a pulse, and remember he had to do this visually. There was no electronics. There was no photomultiplier. There was nothing like this. So whatever they did, they had to do visually or with a film. All right, and what he did was actually a film, and then he got these, and it came out to look like it decayed experimentally. Right? He had the pressure. He knew what the pressure was. Therefore, he knew what the velocity was. If he knew what the velocity was, and he got these sort of curves, he said it was an exponential. Now that seemed to be very good. He got lifetimes like this. This is 1 over the lifetime that he would get, so it's about 20 nanoseconds. He then decided this was a calculation that he had by the theoretical model of an oscillating electron. Now some of you have had that, some of you haven't. Before quantum mechanics, people didn't know how to interpret, for instance, the modern theory where you have the Perrin-Jablonski diagram. Things like this didn't exist, right? Because you didn't have quantum mechanical levels. And so it was an oscillating electron, but you see that these are very close. This is the theoretical value from that, and this is this, so it looked really very good. An oscillating electron means that you've got some sort of a charge that's oscillating. It actually will emit radiation, all right? It's called a Hertzian dipole, and that radiation will decay then after a certain amount of time. This is mass times acceleration. This is like a spring constant for a harmonic oscillator. This is what's called the radiation damping constant. And they knew at that time if you take the radiation damping constant divided by m, you get 1 over the lifetime of the decay of that oscillating electron. And from that you can even get the width of the, and everything comes out right, actually. The times come out about right. Not only the times come out about right, but the width of these things come out right. This is the natural radiative light width. Somebody asked about why you don't see peaks. This natural radiative light width of emission but also absorption is so short and so narrow that it's very, very difficult to measure, okay? In other words, you can't measure it. But you have a lot of different molecules that are fluorescing in different ways. So you never really measure that natural line width. And this is for absorption. All you have to do is start to excite it. And then it emits like this. This is light scattering, right? I think you heard about that yesterday somehow. So if you excite something coming with light, it oscillates the electrons in the molecules, and that oscillating electron emits light. Well, it not only emits light, but you can make a model for not only light scattering, but also fluorescence. And this was done by Hertz, who took Maxwell's equations and showed that. Maxwell actually knew that this happened, but he never lived to see it. Hertz did it actually later. These are some of the original diagrams of the electric field that's very close and around an oscillating dipole. So everything seemed fine. He had tried to look at the lifetimes. He got about the right lifetime that Einstein said he should be at. And what happened? Well, what happened was this, that there were theoreticians who came into the game, all right? And this is Gustav Meade from Meade scattering. He doesn't look very friendly in this picture, but you can get other pictures of him where he does look friendly. But he was very famous, and he was really well known, and you didn't argue with him, okay? That's why I picked this picture. Okay, so he told Wien when he saw his results, he more or less said here, he says, hey, look, photons don't just pop out of molecules. We know that. Why do they know that? Because Niels Bohr had said at that time that you had stable orbits. So and this is a question that I want you to keep in mind. You have a stable orbit, so you have molecules that have a stable ground state, and if you calculate them quantum mechanically, they have a stable excited state. Why should they fluoresce? Why should they come down? They're stable, right? You can't have anything if you don't have a perturbation, supposedly. Okay, so he said that what happened was he had then a paper that came out from him where he talked about the time of emission of the lifetimes. Now, in this, he then said that according to the Meade theory, he said there should be a certain amount of time when the molecule goes in the excited state, and then it stays there for a while. And this became known as the dark state. All right, it not doing anything. It doesn't start to come out yet. The molecule's doing something up there. The electron has to fiddle around before it actually decides to come down. Therefore, he said what you should see is some sort of a buildup like this and then a decay. Okay, so Wien said, okay, rather than go back to these early results here, where he, well, I won't go back all the way, but where he didn't actually see the beginning, he went back and tried very hard to get the beginning, and lo and behold, he saw this. So he said, Wien then introduced what he called the dark time based on the theory of me. So Wien had made the measurements first, everything came out fine. Me came in and told him he should see it in a different way. He made some measurements, he saw something different. Me was very famous, so he took his word, and that became a dark time. Now, I'd just like to point out, before we get too carried away, we have to be fair to Professor Me, because he was actually on the right track, but for the wrong reason. Okay, because if you have, and this was, let's say you take energy transfer, so you excite a donor and you have an acceptor, and then you look at the fluorescence of the acceptor, what do you see? Well, the acceptor is being excited by the donor. The donor is decaying by an exponential. So you're not exciting the acceptor by any sort of a light pulse, you're exciting it by a decay. And that means that it will actually increase first and then decrease in time. And that's exactly what does happen if you look at the acceptor in energy transfer. So it was something similar like that he was talking about. So, and that's due to a convolution. So you're always convoluting, and that was a question that was asked here, you're convoluting the fluorescence output with the excitation form of your, that's actually exciting the molecule. So if you're exciting with something that's not a delta function, you don't get an exponential decay. You get something else that's convoluted with the form of the excitation pulse. That was sort of what he said, although he didn't say that exactly. He just said everything should do that. Okay, there must be something weird inside of the molecules that's making the molecules sit there for a while before they decide to come down. So there we are off to the dark times. And there was about 16 papers that I found that record the dark time at this time. People were making measurements. They would get the measurements that were there, and they would talk about the dark time all the time. And I would like to just give two examples of that. One is by, I don't know how many of you know him, Robert Wood. He was a very famous optical guy. He has a really famous book here called Physical Optics that he published in 1914. He was also an excellent lecturer, things like this. He was quite well known. You can see he's well known here. This is him, Wood. This is Max Planck. This is Einstein. So he ran around in those circles, more or less. And he actually did the following experiment. Rather than doing it as it was done by Wien, he took mercury and then he heated the mercury here. The mercury ions come up very, very fast up this tube because there's a vacuum down here and it's cold. So he knew the velocity of the ions as they were coming up here, the mercury ions. He would excite it here and then take a picture with a photograph of that fluorescence that came out and analyze that. Okay? And he had another way he did it, which was like a synchrophosphorescope, which was faster than that of the original one by Becquerel, where he had something turning. I won't go into how that worked, but past the slit, and doing that slit, he could then look at very fast times. And what did he find? Lo and behold, he found a dark time. Okay? Now you have Wien, who's one of the best known people in experimental science. You have Wood, who there was nobody in the world to compare with optics with him. And you have me, who's a theoretician, telling you what it should be. So people kept seeing this, okay, and they kept publishing. This is the original thing that I showed, that he saw this sort of a dark time. And here in that slit experiment, he also saw a dark time, a time between the time of excitation and when he started to see the emission, that he could see something coming out. Okay, and then he said that, and this became, it was bursting into luminosity. In other words, you put the molecules in the excited state, they were there for a while, and then all of a sudden, boom, they started to emit, right? And this was the idea. Doesn't agree with what we know now, right? At all. But that was what it was, and that mixed up a lot of people. Then, however, came a suggestion for an improvement in instrumentation to go even faster, and that came from somebody who was very famous, known as Lord Rayleigh. Lord Rayleigh actually did make the suggestion that a previous publication early in the 1900s by Le Mans had actually made what we now know as the Kerr cell, which is where you have a certain type of a molecule in solution, and then you put an electric field on it, the molecules orient, and due to the anisotropy decay, if you have polarizers, then you can modulate the output of the light. And you can do this modulation electrically very fast. Still not using electrical detection, but modulating the light, and you can modulate it very, very fast, and then use certain optical techniques in order to measure the lifetimes. And interesting enough, Lord Rayleigh at that time even told him how to do the fluorescence experiment. And he said, if you're doing fluorescence, the fluorophore is here, and this is your lamp, and it's coming in here. If you didn't have a fluorophore, but just reflected the light, and then you had some way of taking a photograph of it, or you had fluorescence light and took a photograph, you see you've got a certain amount of time the light has to go from here to here. So if this is delayed due to the fluorescence, then you'll delay the pulse, and you'll be able to see the delay in the fluorescence light coming out, the short delay in the fluorescence light. Just like was shown in the experiment that Ben showed, you get this delay, and if you know what that delay is. The problem with that is, okay, that you have to do a deconvolution, and I'll talk about that in a minute. And remember, at that time, this is very early, they didn't have computers, they didn't have calculators, they had slide rules, I guess, and logarithm tables, and they had to do everything by hand. Anyway, this is picked up by a guy called Göttling, who actually used that, and he measured similar things using the Kerr cell. He believes me, Wien, and Wood, and comes out with the same idea that there's a dark time. So that was an apparatus which was used. He used the same sort of apparatus that Lord Rayleigh told him that you could do in order to get faster times. We still use it today. As a matter of fact, some of the first, especially time and frequency domain instruments that were ever made, even here on this campus a long time ago, were actually done with a Kerr cell, or in that. Okay, well, his results said it was the same, so it was sort of the dark ages continue. Okay, so we've got the dark ages of fluorescence lifetime continuing. What do we do? Well, along comes somebody, well, this is just sort of fun. Anyway, I make fun of the bursting in luminosity because that's what Wood said. It's obviously wrong, but that was very, very much. So there is a solution, okay? And this solution came from somebody, Gaviola, who was mentioned on one of the slides of Ben. He was an Argentinian. He came to Göttingen, which at that time was the mecca of quantum mechanics. It's where it was really worked on most and discovered by people who were working there. And if you just go through these names, if for those of you who know, things like Max Born, David Hilbert, Richard Courant, Pringsheim, Max Planck, I mean, he worked with all these people. He was actually somebody who spent some time there and worked, so he was a pretty well-educated guy. And he was very, very talented also as an experimentalist. So he did the same experiment. And he used the suggestion from Lord Rayleigh. He used the Kerr cell. This is the Kerr cell here that you modulate. And then he used again the idea of having the variable length in order to change the amount of time that you have that the light travels. Now, the way he did that was then he would have the excitation pulse, which would look like this from the Kerr cell, and then he would change the length of the fluorescence pulse in order to match the intensity of the excitation pulse, so that he could change the time between them and match them. This was all done without any electrical detection. And so what he sees is, and this is where this convolution comes in, if this is the shape of this pulse, then this pulse is made up of a lot of little delta function pulses, if you want, and each one of those delta function pulses causes a decay. And that goes for every single little delta function that you want to think about happening here. This is called, then, this decay here is called the Green's function, and this is the excitation function that goes in a Green's function, for those of you who've studied that. So that means that it's convoluted, and if it's convoluted in there, then even though the excitation looks like this, then the emission will look something like this, right? Or like this, a short time or a long time. And that's what you're going to be looking at. So you're going to be comparing those two times. The problem with that is that you have to know the shape of the pulse. Because if you don't know the shape of the pulse, you can't interpret what exactly the lifetime is when this comes here. So it was a long way to do the actual analysis. But he did it, and he actually showed that that they depend upon the molecular species, according to Einstein's and Schrodinger's theory, depend on the environment. It involved the deconvolution, which he had to do by hand. But if you take a look at these values that he got, they're the values you get today. It's an amazing experiment that he did. So he actually got the correct times. And not only that, just by taking, for instance, things we use now, rhodamine D, fluorescein. This is actually fluorescein type dye. Erythrocin and eosin, which we'll talk about in a minute. Now you have fluorescein, eosin, and erythrocin. They're exactly the same, except this has bromines attached here, and this has iodines attached here. Okay, and that's something that is called intersystem crossing. That's what happens when you go over to the triplet state. And if you increase the rate at which you're going from the singlet state over to the triplet state, then you decrease the time of the fluorescence, right? And that was the first time that that had been shown by him, because he actually measured those with fluorescein, eosin, and erythrocin. Did you have a question, or are you just scratching your head? Okay. And then he showed that in his original data. And he also showed what's called the TIC states, twisted internal charge transfer states. He actually studied these things under different conditions, like different amounts of viscosity and things like that. Well, it turns out when you excite rhodamine B, that these amine groups on the end of the rhodamine B, there's this, let's say this is a plane. So there's a plane, these amine groups sit like this. It goes into the excited state, and there's a certain amount of time in the excited state that these want to turn this way. All right, just because that's the way they belong in the excited state. That takes a certain amount of time. That's sensitive to viscosity. So you can use rhodamine B for viscosity, for measuring viscosity if you want to, by measuring the lifetimes. And he showed that. That was all shown in his original papers. Now we have to ask, okay, what he did was, and I didn't really show too much of that, but he actually did show that the Schrodinger approach, and that there was a real exponential decay, and there wasn't any dark time. That's what he actually showed. I didn't actually go into that in detail, but he showed that. So what was the matter about Wood's early results? Because Wood was a very good experimentalist. He did see those things. Why was he wrong? Well, it turns out that it's just like energy transfer. In what Wood was studying, okay, which was mercury, he excites it to a certain state, and that certain state has to excite this state, and the green band that they're measuring comes from this, not directly from the state that's been excited. So now you see what's happening is the state A, which is going to be this state, all right, it actually decays over to B, and then you're seeing then an increase in B and a decrease like this. And that is how that dark state comes, because it takes a certain amount of time before any luminosity comes out of this particular band. And then he showed that this was the equation that you use, and this is the exact equation that you use to analyze the acceptor in an energy transfer state that you actually have, or anything else that's excited in the meantime. And he went into a whole theory, and he had a lot of things, but he went through the same thing. But he also noted at that time that the classical theory, there's also no decay. There's no dark time, because you excite a classical oscillator and then you let it come down. In that theory, there's none. And in quantum mechanics, there's none. And so he showed that they were misinterpreted. And then he went back and worked together with Wood. All right, so this is a publication that came out from Wood, and they actually showed that it was true that that dark state would be there at that time because of this. So if they were measuring here, they would see it increase. This is the burst of luminosity that Wood talked about, and it came down. It was actually in the data. He just interpreted it wrong. He thought it just came down from one excited state. And so, but that is what you see in those cases. What about Wien's early results? Okay, well, we won't go into it, but a fellow called Port again went back and worked with Wien, and it was an artifact. Okay, it was an artifact of their measurements. It didn't really exist. When he went back and did the experiments, he didn't find this dark state in the interpretation. And Wien worked together with him, and they came out with a later paper saying that. So that's the end of the dark times, okay? And that was actually published at the end of the dark times. Now, how do you actually take the experiments of Gaviola, which I said were very difficult to do, right? I mean, imagine you're sitting down, if any of you have ever tried a deconvolution, and you're sitting down, you want to do a deconvolution of anything, and all you've got sitting in front of you is a slide rule or logarithm tables. Okay, it's going to be a pretty hard thing to do. And so there had to be something done, and we all know Fourier. That means you can take any repetitive function and you can expand it in terms of a cosine and a sine. This is the trick of the frequency domain measurements of anything, actually, and also of lifetimes. So Dushinsky in Berlin realized this, and realized that these repetitive pulses that you were coming out with in the experiments that were originally done by Gaviola could be dissected into the cosines and sine functions, and they're completely independent of each other. When you go into a Fourier analysis of something, then each one of these components is completely what's called orthogonal and independent of the other one. So you can do a Fourier transform if you want, or expand your signal in a Fourier series, which is a lot easier to do. It's not hard to do. That you can do by hand really easily. And so so you could actually make those measurements, and then he said, well, you may not have exact sine waves, but you can analyze this in terms of the fundamental 2 times, 3 times, and each frequency component that you want. And then you get this, which was shown in some of the slides of Ben as being the modulation. And then this is the phase delay that you would get out of this. So you can, by the phase, and you didn't have to know the shape of the pulse, because you could do a Fourier transform of your data. Well, it's interesting to know, this is just showing that he did it in the same way. Okay, he still did not have an electrical way of measuring, right? It still ran over photography and eyes and things like this and optics, but he was able to get numbers out of that, out of his photography, and actually do then by hand do a frequency domain. Well, what's really interesting is that he thanks Pringsheim, who he was working with there, but he also thanks Schrodinger. And you wonder why. I mean, Schrodinger maybe wasn't as bad as Heisenberg with experiments, but he probably never did an experiment in his life. And why would he thank Schrodinger? And I've thought about that, and I haven't found anybody to say this is true, but it's what I've decided, okay, is true. That here's Dushinsky walking down the hallway, mumbling to himself about how hard it is to repeat these experiments by Gaviola, because you have to do this stupid deconvolution all the time. And he runs into Schrodinger, who was a very good mathematician, was working with all sorts of orthogonal functions and everything else in quantum mechanics, knew Fourier series very well, and said, well, just take the Fourier series, take the Fourier transform of your data, and then analyze the different components. Easy. And I imagine that's what happened. That's what I think anyway, okay? So I think that's what he got, because there's no other reason I can imagine why he would thank Schrodinger for that, other than the fact that it was the first time. And this is the beginning of the frequency domain of measurements. So he says here, and this is a translation, for the Gaviola fluorimeter, the theory demonstrates the following possibility. One is free to choose any Fourier component of excitation and acquisition signal, anything, any form, without having to know the actual waveform of the repetitive pulse. And that's important. And that's the real advantage of frequency domain measurements. It's the basis of radios, the basis of television, the basis of everything that we do, a lot of in electronics, okay? It's very, very easy, because we don't have to make any corrections for things. We don't have to deconvolute. And actually, you can do the deconvolution with Fourier techniques anyway. So ever since then, this has been known as the frequency domain of fluorescence. It's easy to analyze with that. Well, there were some other experiments that were done later. For instance, this is one that was by Tumaman, who was in Russia. And this is an interesting one, because what he did was he had a light of excitation. He excited the fluorophore, and he had a semi-mirror here so that he was reflecting some of the excitation light down here. This is the first case that somebody was using electrical detection, because he has down here phototubes, right? The very beginning of phototubes. So what he sees is the light coming through, again modulated. He's using the frequency domain. So he's modulating the light, and here he's picking up the excitation light. Here he's picking up the fluorescence light. There's only a very, very small phase lag between them, because it takes a certain amount of time for the light to go this distance compared to here. And then he puts it in to something that just started at that time to exist, and that's a scope. Right? So then he put in on the horizontal, it has a horizontal axis, right, of a scope to deflect the electrons in a horizontal way, and it has another electrodes that deflect the electrons in the vertical way. And what he gets is, and I'm sorry, I just called it the Lissajous figure. I didn't draw one, but what happens is if they're both exactly at the same time, then you get a circle. And if they're not at exactly the same time, then this will come out at a different time, and you get something that looks like this on the scope. All right? And that angle that you get here in the scope is your phase. And that gives you your lifetime. Very easy experiment. It's the first time that electronics was ever used for measuring fluorescence lifetime. Actually a neat experiment. You can even do this in the laboratory if you want. It's easy to do. You can hook it up to actually do this measurement and put it in on the two different parts of your scope and get a lifetime. No calculations. Okay? You just measure the axis of that loop, and you get the phase. From the phase you get the lifetime, which was covered by Ben, how you get that. This is done later by Bailey and Rolifson, where they again used the frequency domain. Everybody switched to the frequency domain because they didn't have a way of making really short light pulses at that time. Now we do. If you have $100,000 or so, you can go out and buy a 2-photon laser that'll give you femtosecond pulses, and that's fine. You can also buy some nanosecond pulses, even picosecond pulses, but it costs a lot of money. This was done here by Spencer and Gregorio Weber. Gregorio Weber was a very famous person who was here at the university who introduced a lot of fluorescence in the early days into biology. He was the first one to use, he called it a cross-correlation phase fluorimeter. What he was really doing is using heterodyning. How many, this is just interesting, I ask this all the time, how many people here know, just be honest, okay? So you only have to hold up your hand if you know. How many people here know how radio works? Oh, see? Hardly anybody knows anymore. A long time ago, where I came from, people used to build radios and things like that, used to know how radio works. Well, a radio works by what's called heterodyning. Okay, you have radio, the signal for a radio wave is at a very high frequency. You can't hear that, right? You can't hear anything above 10 megahertz, kilohertz, maybe 20 kilohertz now. When you were a baby, you could hear 30 kilohertz, but then after a few weeks, it went down to 25 kilohertz. So you can't, you can't hear those. And so what you do is you mix that signal, that high signal, with another signal that is at almost the same frequency but a little bit different. So what you're doing is multiplying those two frequencies, and what you get is the sum of those frequencies and the difference in those frequencies. So you bring the difference down to a much lower level. And what does this do? It first of all gives you a signal you can work with because it's a nice low frequency signal. It has all the information you had at the high frequency components, and yet you get rid of a lot of noise. Okay, because noise, if you think about being white noise, has a big frequency spectrum, right? It goes from, you know, DC all the way up. If you're using low frequencies, you can put in filters and come all the way down to low frequencies. And that was a big advantage. And so that's what they did, is they used the heterodyning to increase the cross-correlators. Interestingly enough, one of the first things they did use Kerr cells, but they also used ultrasound in order to modulate the light. If you put a standing ultrasound wave in something, then you can modulate the light with that by using the interference of the light as it comes through due to the index of refraction variations. And from then on, I'd say lifetimes lived happily ever after, right? We've had a lot of improvement for lifetimes, but you can see how difficult it was possibly to have that take place. Here's a great scientist, Mark Twain, okay, who I think sort of illustrates the whole thing of what you can't depend on your eyes when your imagination is out of focus. So what happened was they were told what to do. The experimentalists did it. They saw what the theoreticians told them they should see. Everybody believed it. And Gaviola was the one who actually showed us that that wasn't true. And then after that, after these frequency domain techniques came in, and of course in modern days, after you can just go out and buy things off the shelf. So now if you want to measure lifetimes, you don't have to build an instrument. You go to Ben, you say you want to have an instrument, he builds one for you. And you actually can even, if you want to, just push a couple of buttons and see it happen. It's nice to know what happens inside. That's what you're going to be working in the laboratory, but you can do that. So now I would like to spend a little bit of time. What are lifetimes really? Now we know how they come down. What are they? What do they correspond to? Well, this is the way we usually think about it. We excite the molecules somewhere up here. And this goes to your question that you had, because you're exciting to a lot of different states, so you get a big distribution of molecules. And in the solution, they're so close to each other, you don't see it. If you take things down very cold, you do see these lines that you were talking about, okay, so that they don't vibrate. Okay, but if you remember, this fellow here said a long time ago that God does not roll dice. Well, the problem with that is that he does, okay? And that means that there are certain things about the lifetimes that we have to think about to really understand what is a lifetime. So now that we've seen how to measure lifetimes, we know that they decay exponentially. What are they? And what do they correspond to? Well, there's the one who told us, right? 1917. He told us, using thermodynamic arguments, that the lifetime was what he called the A coefficient. You bring something from the ground state up to the excited state. That's the excitation. That involves light, right? You bring it down from the excited state to the ground state with what's called stimulated emission, which is what a laser does. That means you stimulate the molecule to come down to the ground level and emit a photon. That's what a laser does. That's why a laser works coherently in that way. That takes a photon, right? That takes light to do. But there's another way for it to come down, and that is spontaneous. It just decides to come down by itself. And the question is why? Well, Einstein didn't know why, but he told us how to calculate it. And he told us how to relate it to essentially the absorption coefficient. Okay, that was 1917. That's why all these people started measuring this. As a matter of fact, apparently Gaviola knew Pringsheim very well in Berlin, and Einstein knew Pringsheim and asked Pringsheim to find somebody who was good to measure lifetimes, because he says, after all, I calculated this about 10 years ago, and nobody's been able to measure it successfully. Okay, well, we go into quantum mechanics, which is called, it's actually Dirac's golden rule, not Fermi's golden rule, but we won't go into that right now. It's an interesting thing, but you have it on your computer now. But there's such thing called a matrix element, and what this means is this is now quantum mechanics, so that takes into consideration you actually do have a ground state and an excited state, and they're quantized. This is the way that it's usually calculated. However, usually the way it's done in any classes until you get more advanced is to assume that the light is continuous. It's a wave. Is light a wave? No, it's a photon, right? So it's also quantized. But in the beginning, people didn't do that. They thought of light as being a modulated wave. And this is how you calculate. It comes out right, exactly right. If you put this in here, and this is what's called the matrix element. It actually has the, I think it's on the next slide. I guess it's not on the next slide, okay, but it has the ground state, the excited state in it, and then it has the dipole operator which hooks them together. But that requires it to be a perturbation. That is the way it's usually done. Quantum mechanics, interestingly enough, cannot predict spontaneous emission. It just can't do it. There has to be a perturbation in order to bring the two states together. So there's something missing there, and however, there's something called the density of light modes in a cavity. And these are modes where there's no light. For instance, in this room, we now have light. If we turn the light off and it's completely dark, there are still all those modes out there. It's just that there's no photons in those modes. And each one of those modes, believe it or not, even though there's nothing there, supposedly, according to the theory, this is exaggerating a little bit, but it has 1/2 of the wavelength, 1/2 of the energy of a photon that it would have if it was in that mode. And what you do with the light is when you put photons, when they come from a molecule out, they go out into one of those modes. And since light is a boson, you can put as many photons as you want in any mode. All right, so you've got these modes coming out, and that's the way, we won't talk about absorption, but what I mean to say is that even if there's no light out there, there are modes there. And these modes do have what's called, it's a background energy, and this fluctuates, believe it or not, even though there's no photon in it, and that is what gives the perturbation for the light to come down. That's called quantum electrodynamics, and that is this is where we actually see the transition moment, where we are putting the initial state together with the final state according to quantum mechanics. So we know. We took a long time, right? I mean, people measured it, they argued about it, they had classical methods of calculating it. The Fermi golden rule was created before they actually knew about the quantum electrodynamics of those. And I'll let you read this in the stuff I put there. These are two really nice papers that a lot of you with a little physics background can read. Meloni, he's a very nice theoretician. He works in I don't know if it's Lawrence Livermore Labs, I think now, and that's where he works. And he's a theoretician, but he writes a lot of things that are a little bit more educational, and he explains that. I think you're going to have some of this later, because when you talk about metal-enhanced fluorescence or plasmonics and things like that, what you're doing is changing the density of the modes that are outside the molecule. So since the emission of a photon, if you have a molecule in an excited state, like I said, there's no way for that molecule to come down if it's not perturbed. It's perturbed by the fluctuations in those modes. Okay? And the more modes we have per volume, so to speak, the more density of modes that we have per volume and per frequency, the bigger chance there is for that energy to go to that mode. It's just like a chemical reaction, right? You have more stuff out there, it reacts better, and it goes out into those modes. So by increasing the number of modes per frequency that you have outside of your molecule that's excited, so to speak, and you can actually lower the fluorescence lifetime. And this is what's done in metal-enhanced fluorescence, a lot of plasmonics and things like that. You can control that because you can control the lifetime. And this is something that recently has taken place, and I'm pretty sure that you're going to get some things about that. Okay, now the last thing I have to cover in the first part of this lecture, because you didn't realize that maybe, but I have two lectures to give, so I don't have to go through all the rest of the slides right away, is what is hidden now in a lifetime. Now we know what the lifetime is. Why is it useful? I mean, after all, to really get down to it, other than the fact that it's intellectually stimulating and academically exciting, do you really care what a lifetime is, theoretically, that we've talked about in quantum mechanics? You want to use it, right? You want to use it in microscopy. You want to use it for whatever you're using for. And that's what we want to see. Now, that was actually told to you also already by Ben, but I'll repeat it. This is an easy way to remember just about everything that happens in a fluorescence measurement, okay? So what you have is you have what I would call an excited state room. And you have a photon that comes in, and that molecule has gotten a photon. It's now in the excited state. That, let's take into consideration, first of all, it only has one way to go out, so it has a certain rate to go out here. And I like to make the example, it's a horrible example, but I'm going to do it anyway, that I have you all here in the room, and let's say I have just one of you in the room, or I can have you all in the room. And I come in the room right here, and I put a package down on the table in front here, and I tell you, well, I'm sorry to tell you, but there's a bomb in here, and I'm going to go out. And I turn off the lights, and I know how to get out of the room, and I leave. And you get really excited. So you run around the room, bang off the walls, and everything else. You can't find your way out. Finally, you get out that door, right? Because there's only one door to go out. And you think I'm a nice guy, so I tell you, don't worry about it, just come on in, I won't do that again, and I do it again. And you get excited again, and every time you go out, I stand out that room and I time you how long it takes you to come out. Okay? Now, guess what happens if you come out of your room? Guess what it looks like when you're actually going to come out? I guess you can't see this, right? I don't think I can move this around, right? Well, never mind, you can't see it. So what happens is, if I just say I got so much time and I put it on a scale, it'll have like an exponential going down, right? That is the amount of time it took you out. The probability of you getting out that door will be bigger at the beginning and longer time you are in there at the end until the bomb explodes, and then you don't come out, which is what happens to a molecule when it's in the excited state and it has photolysis. Okay, so but the thing of it is that this rate never changes, ever. Okay, in your experiments, the rate of fluorescence never changes. It just comes out and emits a photon like this. And it's a random process, and it gives an exponential decay. There's a reason for that. That's in your notes, and I'll let you go through this. It has to do with probability, but you can show from probability. And the reason I show this for you to read is that if you have a single molecule, you can't write down a differential equation. Okay, that's what's usually done in books. You write down a differential equation showing it's an exponential decay. Single molecule, you can't do that. It's a probabilistic event. It's a random event. So you have to use this sort of an argument. Well, we won't go through it because too many details, but you can prove that it's an exponential decay. The real use of fluorescence comes here because there's a lot of different ways. I can come out and I emit a photon, or let's say you go out the room. But let's say that I stand out there where you went out that door, and let's imagine, oh, there's another door here. So you find another door open, okay? So now, rather than just leaving that door open, I also open this door. But I'm not watching you go out that door. I'm just watching that door. Can I tell that this door is open? Yes, right? Because I can ask, how long does it take you to get out of the room? Sometimes you go out of there, and sometimes you go out of there. So you go out of there fewer times, but the time it takes you to go out that door is decreased. And also the number of times you go out that door decreases. That's the intensity. So that means I can do this with as many doors as I want. And I can tell your kinetics of going out this door by measuring the lifetime or the rate constant of going out that door when this door is closed and when this door is open, without ever measuring that door. Right? I only measure that one. And that's the trick in fluorescence. And that's the reason why we're really interested in fluorescence. Now we have a lot of different things that can happen. Like Ben said, internal conversion, intersystem crossing to the triplet state, energy transfer. We can measure all of those. And in the excited state, the lifetime is the addition of all of those rate constants, just like the lifetime or the rate constant for coming down from the excited state is actually the same, is actually a contribution of all the different ways of doing it, going out the doors. And including this, which I may talk about later, I'm not sure. Photobleaching is usually a pain because you get rid of your molecules, but you can use photobleaching, believe it or not, to also measure any of those rates. As a matter of fact, I'll just mention it, and if some of you want to ask during the coffee or something, you can measure something like energy transfer without ever measuring fluorescence. And as a matter of fact, you can measure it with mass spec. You can measure it with you can go in the lab and use photolysis in order to measure the rate of energy transfer, and it's actually done in that way. It's a very easy way. If you have, for instance, if you work with microscopes in your laboratory, and you want to measure the rate of energy transfer, the real rate of energy transfer, and you say, well, I can't do that, I don't have all this expensive equipment, but if you can just photolyze the particular place where you are in the presence and the absence of the acceptor, you can measure it, all right, and you can measure the rate that's going. So the important thing is that the total rate is greater when you have more pathways open. So the quantum yield of energy transfer, for instance, is dependent upon what you put up here. You can actually measure the total number of energy transfers divided by the total number of originally excited molecules just by measuring the lifetime of fluorescence in the presence and the absence of the transfer. That may be, if you follow what I gave you in here, it's pretty straightforward to derive that. Okay, so you can determine P, in other words, a pathway P by measuring M. And that's what you do. You're measuring fluorescence. Fluorescence would be M, and you can measure the kinetics of that. So it's simple. And that's the reason that we actually use fluorescence in general, right? Because we're not, some people are, some of us are, but a lot of people are interested in using fluorescence to find something out. And the reason that that works is this. All right, and so you can pretty well interpret almost all experiments, and that gives you then this, all right, where we use the lifetime of fluorescence, and now we've been able to see how these actually develop. That's the end of session 1. I'll give you 5 minutes to rest, and then we'll go over some lifetime imaging, because I want to show how we use imaging, how we measure lifetimes in a microscope, in a whole image at every pixel at the same time. And we'll talk about that and how we can use it. Does anybody have any questions at all? You guys are not a whole lot you could ask about history, I guess. I don't know.